Alright, so this is going to be our final geometry lesson. So before we get to what the lesson is really about, which is area and Pythagorean theorem, I wanted to address something that was on your geometry glossary just to make sure that you got this part correct and that you understand kind of how it works. So we're going to look at the sum of the interior angles of some different common shapes. Again, this was on your geometry glossary, so hopefully you already know the formula, but we're just going to test out the formula and see if we think it checks out. So we're going to look at a 3, 4, 5, and 6-sided figure. I think we'll get a flavor for the formula by looking at these shapes, but just know that we could continue talking about other size shapes as well. Okay, so the sum of the interior angles of a triangle add up to 180. We've been talking about that for a little while. The sum of the angles in a quadrilateral add up to 360. Think about like a rectangle. If you have 4 right angles, that's 360. Now, all quadrilaterals don't have to have 90-degree angles. I was just giving you one example. They add up to 540 degrees with a 5-sided figure, and then 720 degrees with a 6-sided figure. And so notice we have a pattern, right? We start at 180 for 3 sides, and then we just kind of keep adding 180 degrees. But let's say I wanted to ask you about, say, like a 20-sided figure, and you didn't want to have to list this table down to 20 figures. That's where a general formula comes in handy. We know it has something to do with 180, right? But we don't want to say it's 180 times the number of sides, because that would mean that it should be 3 times 180 for a triangle, okay? So actually the general formula is 180 times n minus 2. This is always the sum of the interior angles. And n is the number of sides. Okay, so let's kind of check that out. In other words, let's use the formula. So if we use the formula here, 180 times 3 minus 2 in parentheses is 180, so we're good there. This would be 180 times 4 minus 2, or 180 times 4, that's 360. So I think you can see that that formula is going to work, right? 180 times 5 minus 2 works, and the same with 180 times 6 minus 2, that would be 180 times 4, which would be 720, okay? But on the test or something, I could ask you about, say, like a 18-sided shape, okay? And to find the measures of the sum of the interior angles of an 18-sided shape, you would just plug 18 in for n, and then get whatever 180 minus 16 would be. Okay, so we're going to start talking about area. And rather than, I want you to consider in your classroom, you know, the more you make students memorize, frankly, the more opportunity they have to forget something that you wanted them to know. And so I want us to look at an example where you could have your students come up with the formulas on their own. So we're going to start with the area of a rectangle. So I'm going to put this shape here. So notice the area of a rectangle, of course, hopefully we know the formula for this. The formula is length times width. Okay, so let's just look at an example. So let's recreate that note card I just showed you. So if we had a rectangle that was 10 by 5, then the area would be 50. And then when we don't know a measurement, we just say units squared. Okay. So rectangles are formulas that students usually remember. But what about when you get to a different type of figure, like maybe a parallelogram? Now, I like to say that a parallelogram is really just a slanted rectangle. Okay, so this is a parallelogram, right? Parallelograms have both sides parallel. But I want us to take this same example, so let's take a look at this note card. And let's consider that I decided to cut the note card up, like so. Okay, now notice, I'm going to move my original one out of the way. I definitely didn't change the size of the note card, right? The note card still has the same area. It's still the same size note card. But if I were to move this side over, okay, notice the note card is still the same, right? It's just this area that was here got repositioned over here, okay? And in fact, if you notice, the measurements aren't even different, right? It's still 10, but instead of looking at this length, we could just look at the height, okay? So the formula for area of a parallelogram is base times height. Just so you know, h always refers to the perpendicular height or the straight up and down height. That's really going to be true in all formulas in geometry until you hit, you know, junior high math when you're doing volume and you talk about slant height, but for us, we're not doing any of that. It would just be the height. Okay, so notice the area should still be 50, right? Okay, so let's just kind of, I want you to kind of have this in your notes, so let's kind of recreate what we showed with a picture here. Notice this was still 10 and this was 5, right? But then we cut this little piece off and made it 4 by 6. And then we changed it into a parallelogram by moving this piece. So this was still 10, this was 5, this was 6, and this is 4. Okay. Note that the area has not changed, right? The area is still 50 units squared. Okay, so I'm going to put those off to the side for a minute. So notice that we didn't take away or add to the area. So all we did was really reposition it. Okay, we just moved it around. So I always like to tell my students, if you know the formula for the area of a rectangle, which most of them do, then you can actually get the formula for the area of a parallelogram as well. Alright, so let's look at trapezoid. Now before I give you this formula, let's show another way that you could kind of have your students come up with it on their own. So again, let's take this same shape. Now there's different ways to draw trapezoids. Okay, the main trapezoid most people draw is the one that looks like this though. Notice again, did I take any area away? I did not, right? It's still the same note card. I just flipped this piece over. Okay, so how am I going to talk about this? Notice I have a 6 on the top, right, and a 14 on the bottom. Those two are called the bases, but my height is still 5. So I need some way to kind of talk about that. So I have a base of 6 and a base of 14. Notice if I talked about what the middle of 6 and 14 are, though, notice that would be 10, which is what I'm looking for. So if I just do 1/2 times base 1 plus base 2, and then times the height, okay, then that will give me what I want. So again, I'd like you to have this in your notes. So this is what we had, right? We had a 10 by 5, and then we cut this piece off, this part being 4, this part being 6. I know I'm not necessarily to scale here, and then I ended up with a trapezoid with one of the sides being moved, right? So this was 5, this was 4, this was 10, and this was 6. Okay, and note that the area is still, it's going to be 1/2 6 plus 14, right, times 5, which is still 50 units squared. Okay, most of the time, just so you know, you're going to see the area formula for a trapezoid written just a little differently. Usually we move the height to the front. But I like showing it in this original way just because it shows that it's truly the average of the two bases. Because that's really what's going on there. That's why you have the 1/2 base 1 plus base 2. So notice in all three cases, right, we have common formulas, but we're really just talking about really the same area just moved around. Okay, we also have the formula for the area of a triangle. This is another one that students often know. Okay, you could use your note cards again, right? Notice that if I cut this in half, I would have a right triangle. Now that's not the only kind of triangle I can have, but the formula for area of a triangle is literally kind of like the formula for area of a rectangle cut in half. Again, h is the perpendicular height. And then the one kind of oddball I want you to know for this section is the area of a circle is going to be pi r squared. Okay. Make sure you know that r is the radius of a circle. It is halfway across the circle. I think there's just one C and a cross there. All right, so the point is that I think you can do problems where you don't hold their hand and give them every formula they ever need. Okay, it's sometimes more helpful for them to, instead of memorizing, because the problem with memorization is when it fails entirely. Okay, in other words, if you ask your students to memorize a 10-step process and they forget step 4, they're kind of dead in the water. So I like to give my students more of reasons why, so that when they're stuck on a test or they're stuck somewhere where I'm not there to help them, then they can hopefully use their logic and their reasoning skills to try to figure out, you know, what the formula was or what the answer is or how to find it when maybe they're not sure what to do. Okay, frankly, that's preparing them for, you know, life after your class a little bit better when you don't always tell them, oh, now we do step B, now we do step C. Okay, that's not necessarily the only type of problem solving they need to be able to do. Okay, so we're going to look at some areas of maybe some unusual shapes that we're not sure how to find the area of. And these are great kind of problem solving questions because, again, they're not cookie cutter problems. They require that the students think a bit. So let's say that I give you the following measurements. So let's say that I give you that this is 10 meters. This will not be to scale. Let's say that I tell you that that this is 16 meters, that this is 20 meters from here to here, and that this is 4 meters. And I say I want you to find the area of, we call it a composite shape because it's more than one shape possibly put together. So there are many ways you could split up this figure. Always try to split it up into the smallest pieces that you can, okay, or the least number of pieces that you can. Notice that this is a trapezoid turned on its side. It's actually a right trapezoid from your glossary. And this is a rectangle. So the area of a rectangle, we'll start there, is going to be length times width, right? So the area of this rectangle is going to be 16 times 10 or 160. So if you have room, you can work it inside the shape, okay? But maybe we don't have room for the trapezoid, so let's work that off to the side. So remember, the formula for area of a trapezoid is 1/2 height times base 1 plus base 2. Okay, so let's go ahead and label some of the things that maybe we weren't given. Notice if this is 10 meters over here, then so is this. So now let's see if we can figure out what this length is, right? Well, if from here to here is 20 and from here to here is 16, then this must have been 4. So just pay attention that if you have the trapezoid turned on its side, the bases are parallel to each other and the height will be perpendicular to those. So notice that 4 meters is the height, right? And then if we take the sum of the two bases, this base is 4, this base is 10. So you end up getting 2 times 14 or 28. Okay, so I'm going to circle this guy too. So then the total area would just be 160 plus 28. Now in the end, make sure that you put the measurement. Notice I didn't do that along the way because I was kind of pressed for space. Okay, but technically speaking, we would want meters squared or whatever measurement it is squared. If you're not given a measurement, then you just say units squared. All right, so let's do another one. So let's say that you were given this shape and asked to find the area of this weird thing. Now notice, I could mark this off as a trapezoid and a rectangle this way if I wanted, but I actually think it would be easier. Well, first let's get the measurements. I guess that would be helpful. So let's say this is 9 inches. Let's say from here to here it is 18 inches. Let's say the base is 10 inches. And then this is 6 inches. Okay, so let's go ahead and mark this off. Okay, so now notice we could probably use some measurements here. So if this whole thing's 10 and this is 6, then this would be 4. Okay, and then notice over here, if this whole thing is 18 and this is 9, then this would also be 9. So that 9 plus 9 would be 18. So notice we have a rectangle, right? And we have a triangle here. So when you don't have room to work the problem, just make sure you work it somewhere. So again, the area here is going to be length times width, right? So make sure you pick the right numbers, right? We wouldn't want to pick 6. That's not the whole width of the rectangle, but it'd be 10 by 9, right? Or 90 inches squared. The triangle, the area formula would be 1/2 base times height. Okay, I think we already did the work to find all of those. So 1/2 4 times 9, okay, or 18 inches squared. So in the end, make sure that you show me some work on a problem like this for the homework, but it would be 18 plus 90 or 108 inches squared. And then the last type of problem that you might have, maybe not these shapes per se, but you might have a problem where you're asked to find the shaded area. So let's look at this. So maybe you have a rectangle that is 20 inches by 12 inches. And then you are told that the radius of this circle is 4 as well as this one. But you're asked to find the shaded area. Now notice that's a really funky shape if you just look at the shaded area, right? But I think we can use some existing shape formulas to go ahead and figure out what that shaded area must be. Okay, so because we're not going to do this one maybe the same, if you're not going to show it in the problem, I'd like you to make sure you label what you're doing. So let's find the area of the rectangle first. Okay, so that will be length times width, or 20 times 12. So that'll be 240 inches squared. And then let's find the area of each circle. And then we could just double it. So the area of a circle is pi r squared. Bless me. All right, so if you work that out on a calculator, pi is 3.14 and then a bunch of decimals, right? So 3.14, so it's going to be pi times 4 squared. So that is going to be approximately 50.265 inches cubed if you punch that in your calculator. And then if I want the shaded area, notice I wouldn't want to add these, right? I would want to take the bigger area of 240 and minus the twice the smaller area. Okay, twice because we're talking about two circles. And then in the end we get approximately 139.47. You're always going to have approximate answers when you're talking about measurements for circles because pi is not a pleasant number. All right, so I think that'll take you through most of the area problems. Now, there may be an area problem or two that require that you use Pythagorean theorem, which is what we're going to look at next. Okay, so just know there may be some area problems where you're being asked to combine the two topics for the lesson today. All right, so Pythagorean theorem is a really commonly used theorem in geometry and algebra, in trig and all kinds of stuff. Okay. Usually we introduce this though in junior high math because we start talking about kind of pre-geometry in junior high math. But it is used to find the lengths of the sides of right triangles. So make sure you know what it's used for. I have some students who can always spout off what Pythagorean theorem is, but it's not used for all triangles. It's only used for right triangles. Okay, and you probably know this, but A and B are what we call legs of the triangle, and C is called the hypotenuse. That means it's the longest side. So we're not going to do any Pythagorean theorem problems that are just straight up Pythagorean theorem. In other words, they're all going to be kind of problem solving where you have to figure out, you know, yeah, I need to use Pythagorean theorem for this. Okay, so let's look at just a couple of those, and then you should be able to do the homework from there. So there is a ladder leaning on a 15-foot high building. The ladder just reaches the top of the building. And is 17 feet long. The base of the ladder is 8 foot from the building. And I want you to find the height of the building. So this is a really common problem that you'll see in, you know, standardized testing all over the place. I've seen this on, you know, 8th grade STAR tests, okay? And I've honestly also seen it on, you know, like ACT, SAT, pre-SAT, those kinds of things, okay? So this is definitely kind of an upper level question, okay? As far as it's not necessarily elementary school, but remember, you're supposed to know a lot more math than your elementary school kids do, right? So that's kind of, that goes without saying, right? So this is what I want to know the height for. My artistic skills are lacking, I know. And so here's the ladder. And we know that the ladder is 8 feet from the building, right? And we know that the ladder is 17 feet long. So the first thing is just common sense tells us that this answer is not going to be as long as 17 feet, right? Because the hypotenuse is supposed to be the longest side, okay? So first of all, you do need to confirm that we have a right triangle. You don't use Pythagorean theorem if you don't have a right triangle. But notice, we're going to assume that, you know, the builders built right angles. Sometimes that's a, you know, too big of an assumption, but we're going to assume that that happened. So we will use a squared plus b squared equals c squared. You just need to decide what goes in for what, right? So we do know the hypotenuse is 17 squared, Okay, we know one of the legs is 8, and to be honest, it doesn't matter which one you plug that in for. You can plug it in for A or B. It doesn't matter because it doesn't matter what order we add numbers. So now let's work this out. So this will be 64 plus b squared equals 289. Okay, and then we're going to subtract 64 from both sides. So we're going to get b squared equals 225. Okay, but notice I don't want b squared, right? I want b. So b technically would be the plus or minus square root. So I'm going to go ahead and say plus or minus square root of 225. But to be honest, we don't need to worry about the negative, right? So in the end, we ignore the negative and we just get 15. In this case, 15 feet. Okay. So notice that problem I didn't hold your hand and say, hey, use Pythagorean theorem, but you still were able to use Pythagorean theorem to solve it. All right, so let's do one more kind of thinking outside the box kind of question. So let's say that a student makes a two-dimensional house shape, and he glues it to a piece of paper, and he makes it out of toothpicks. I'm just going to say assume right angles. In other words, things that appear to be right angles are right angles. And I want you to find out how many toothpicks he needs. All right, so I'm going to draw the shape that he had, and the roof is drawn not symmetrically on purpose, just FYI. And let's say that this is 7, this is 4, this is 3, and this is 6. So I'm going to use another color and see what we can fill in here. So notice this is not drawn to scale. Okay, so lots of my pictures aren't drawn to scale. So if that is 6 on the left, it's 6 on the right as well. Notice this is 7 plus 4, so this down here is going to be 11. Okay, notice we need all of these things to find out how many toothpicks there are. Okay, so the number actually represents toothpicks. Okay, so we're actually not only going to need to know, by the way, this is a right angle because it said that it was, but we're going to need to know right here and right here. Okay, in other words, we're going to need to do Pythagorean theorem, so let's do it here first. So here we have 4 squared plus 3 squared equals c squared. So if you add those up, you get 16 plus 9, which is 25. So it looks like C is 5 in this case. Okay, so I'm going to go ahead and label that. That's 5. It takes 5 toothpicks to line the rooftop there. And then notice I could do the same process here. But here I'm not going to get as pleasant of answers. So 3 squared plus 7 squared equals C squared. So I'm going to get 9 plus 49, which is 58, equals C squared. But I don't particularly want that, right? I want the square root of 58. So notice this is not going to come out nicely, so if you use your calculator, this is about 7.6. So I'm going to write this up. So all of these represent how many toothpicks we have. So if we want to count how many toothpicks is required, let's just start adding them, and it doesn't matter what order you add them in, just make sure that you get them all. So I'm going to start here and kind of work my way around. So 6 plus the 11 down here, plus the 6 there, plus 7 plus 4 for this, plus 3 plus that hypotenuse, which was 5. And then when you get to the final one that's a decimal, I'm going to bump that up to 8. Okay, so maybe you can figure out why, but we can't use a partial toothpick. I mean, we can use a partial toothpick, but we have used the whole thing, right? In other words, like, you can't put it back in the box if you don't want to, you know, make your mom really mad. Okay, so in the end, if you add all of those up, he used 50 toothpicks. Who cares that one of those he only used partial? Okay, so notice this problem not only asks you to do Pythagorean theorem twice, but it also asks you to have some reasoning skills, right? I can't use a partial toothpick, so I'll have to bump that up to the next whole number. So for your homework today, the Pythagorean theorem questions are not going to be hand holders. I'm not going to say, okay, here's exactly how you set up Pythagorean theorem here. Okay, but if you notice that, hey, I have a right triangle, then it's probably going to be using Pythagorean theorem. So just make sure that you read the problem, that you answer what I'm asking for, and you should be good to go.